Now, one of the things that we can do with the mean value theorem is prove some of the results that we already seem to know in calculus already. And the first one is this first corollary, corollary 1, which just says that if you have a function f mapping from some domain to the real number system, and it's continuous on a closed interval and differentiable on an open interval, and you know that the first derivative of f is 0 for all the x inside the interval AB, then we can prove that f of x is a constant function. Okay, we know if it's a constant, then f prime is 0. That's not what we're trying to say. We're not saying that if f of x is c, that implies f prime of x is 0. That we know. We're actually proving the opposite result. That is, so this isn't what we're proving. What we are proving is that if the derivative is equal to 0, then that means that the function that we're looking at is a constant function. So the only functions who have a first derivative equal to 0 are constant functions. Now, in order to prove this, what we do is we start with some x in the interval AB, and we apply the mean value theorem to the function f on the interval a to x. We can do that because if f is continuous on the closed AB, it's continuous on x. So f is continuous on closed AB will let us know that f is continuous on a to x because it's a smaller interval. And if f is differentiable on the open interval AB, then we know it's differentiable on the open interval ax. Okay, so by the mean value theorem, we know that there is points. So by the mean value theorem, there is some c value in the open interval AB such that, if we look back at the mean value theorem, we basically, we have it right over here. We have to use this little statement over here such that f prime of c is, now in this case, the b is x, and the a is still a. F of x minus f of a is x minus a. But we know that f prime of c is 0 because that's the function we're dealing with. We're dealing with a function which the first derivative is always equal to 0. So 0, which is f prime of c, is f of x minus f of a over x minus a. And that must imply that f of x minus f of a is 0. In other words, f of x is equal to f of a. Now, there's nothing special about x. X could have been any point. That's what we said at the beginning. X is any point in the interval AB. In other words, f of x is f of a constant for all x in the interval AB. Okay, so we've just proven by the mean value theorem that if a first derivative is equal to 0, then that function is a constant function. Now, it seems kind of a weird result. It's actually quite theoretical, and that's really what the mean value theorem is for. I wouldn't really worry so much about past paper questions like this. It's not really something the IB is going to ask you, but it's good to know where some of these things come from in mathematics. Another corollary of the mean value theorem, actually it's a corollary of the corollary, I think, because we're going to use corollary 1 to prove corollary 2, and that is that suppose that f and g are two functions that are continuous on a closed interval AB and differentiable on the open interval AB. If f prime of x is equal to g prime of x for all x in AB, then it must be that f of x is equal to g of x plus the constant. Basically says if the slope of the tangents are equal for two functions over all values of x in some interval a, then the two functions must only differ by an additive constant. In other words, one function is a vertical translation of the other. Okay? In order to prove that, we'll just set up a function called h of x equal to f of x minus g of x, and simply look at the derivative of h prime. Well, h prime would be f prime minus g prime of x, since h is defined to be f minus g. Now, since f prime is equal to g prime, we know that this is equal to 0. So h prime of x is 0 for all x in the open interval ab. And we just proved above that if that's the case, so by corollary 1, h of x is a constant function for all x in AB. That's what we just proved. I'll highlight that, and maybe not in pink. In yellow, we just proved that right here. So h of x has got to be a constant function. So that means, therefore, f of x minus g of x is a constant, which just is what we were trying to show, that f is g of x plus a constant. Okay, so what does the mean value theorem tell us is that when you're doing antiderivatives, okay, if a function has an antiderivative on AB, it means really what that means is there's some function whose derivative is equal to little f. So big F is the antiderivative of small f, means f prime of x is equal to little f of x for all x in AB. What the corollary number 2 tells us that is that if a function has an antiderivative f, then f is unique up to the addition of a constant. So if you find an antiderivative for f, and it happens to be, for example, I don't know, x squared, then there's no other function apart from x squared plus the constant that could also be the antiderivative of f, right? So to put that in more succinct notation, if I had, say, f of x was 2x, then big F we know is x squared, but it couldn't be like x squared plus x or x squared plus 3x. It could only be x squared plus a constant. Okay? In order to prove this little result here, it seems kind of obvious, but we can give it a bit of a proof here. We'll just say that if you had two antiderivatives f and g, that would mean that big F prime was little f, and big G prime was little f. Or in other words, f prime of x would equal g prime of x for all x in the open interval AB. And we just proved by corollary 2, so by corollary 2, what that implies is that the only difference between f of x and g of x is a constant. And that's why when we have a function like f of x and we say, well, we're looking for the antiderivative of little f, once we know a function that's equal to it, every other function, so if it happens to be that big F of x is the antiderivative, every other antiderivative is big F of x plus a constant. And that's why we can talk about the indefinite interval of f with respect to x, as opposed to an indefinite interval of f with respect to x. And that kind of finishes our note off for the Rolle's theorem and the mean value theorem. And to get some practice on this, what I suggest that you do, I posted that on Veracross, but let me just write it here so it's perfectly clear for everybody. What I suggested that you do is some homework, okay? And these homework exercises are in the Hayes and Harris option book. And in exercise F, there are 4 questions, 1 to 4 to do. Okay, now if you can't remember where to get the Hayes and Harris book, it was available on Veracross. So if we go to our class's website here. I can remind you of that, where that is. I think you need to go back. Oops, that's not us. That's the grade 11s. Excuse me. This one here. Right, if you go back to the differential equations page, you click on the icon for the Hayes and Harris book, and then you can see it, and you can download this onto your computer as I've suggested before. And you're looking for exercise F. So if we just move up to exercise F, I think we'll see it. Still at C, we're getting there. E and exercise F. Okay, Hayes and Harris has some nice explanations as well as the mean value theorem. So if something you didn't understand in today's video, you could go through that. I followed it pretty closely with my notes so that you could go back and take a look at it. And these are the 4 questions in exercise F. Number 1, you've got to determine whether or not Rolle's theorem applies to the function. And if it does, find out all values of C for which f prime of C is 0. You can do anything you want to determine where f prime of C is equal to 0. That's completely up to you. Okay. And there's question 2, question 3, and question 4 gets a little interesting. Yeah, I think you guys can handle that, and I'll leave that up to you. Any questions for those, please post them on our homework help page, and then in tomorrow's session, I will answer some of those questions.